Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue with solving logarithmic and exponential equations and inequalities. In this one specifically, we're going to focus on logarithmic equations and their inequalities as well. A few notes here. When solving logarithmic equations, you have to remember that logarithms have restricted domains. And this ends up being a major issue when you're solving logarithmic equations because you'll get to answers that you might think, without checking, that they're correct, but because you didn't check, those answers might cause the argument of the logarithm to become negative. And if that's the case, then that is not considered a solution because logarithms can't have negative arguments or zero arguments as well. So that's something to be hyper aware of as you're solving logarithmic equations. Otherwise, what you're commonly doing when you're solving log equations is using properties of logarithms. So let's go ahead and dive into this guy right here. You want to isolate the x values here. So I'm going to go ahead and move everything with x's to one side of this equation. So I'll just subtract log base 2 of x from both sides. So I have log base 2 of x squared minus 3 minus log base 2 of x is equal to 1. Now, there are a couple tactics or a couple pieces of advice I can easily see another instructor giving. Some instructors might say from the get-go, state the domain of each of these separate logarithms. So this is kind of an aside, but if you start by stating the domain of that highlighted logarithm and then the domain of this highlighted logarithm, it somewhat allows you to know if your final solution is going to be correct or not. However, it's often just a little bit easier to wait till the very end to check your work. So I think I'm going to go about it that way. You can start by stating what your domain restrictions are. For example, I'm just going to go ahead and say it. This guy right here has a restriction that x must be positive. The other one, the one on the left-hand side, tells us that x squared minus 3 must be positive. And this is why I think it's much easier to check in the end, because a lot of students struggle with solving a quadratic inequality. This is just a parabola shifted down 3 units. So it looks like that. And you just want that parabola to be above the x-axis. So you're actually wanting this solution. Let me zoom in here. You want the x values that lead to these branches here. And those x values are everything greater than square root of 3 and everything less than a negative square root of 3. Well, the fact is that you can't have anything less than a negative square root of 3 because we're requiring that x be greater than 0 as well. So it's really going to be the intersection of x being greater than 0. Here's 0 right here. So you want all these values. And x being greater than square root of 3. Here's the square root of 3. And you need all these x values. So the intersection of those two would be everything greater than the square root of 3. Those are the possible solutions. They're not really solutions actually, but that's where our solution has to lie. Again, that's not how I would do it, but that's how some instructors would do it. Have you check for domain issues from the get-go. Now going back to our problem at hand here, I'm going to go ahead and use the property of logarithms where we can combine these two logarithms. Because there's a subtraction, it ends up being the quotient of, or the fraction involving x squared minus 3 divided by x. Now that you have all the expressions with x kind of grouped together in a single statement, now you can use the fact that 2 raised to the first should equal the interior. So 2 raised to the first, this is just by definition of a logarithm, 2 raised to the first must equal x squared minus 3 over x. Now, multiplying both sides by x, so I'll just write that, you get 2x is equal to x squared minus 3. Just want to say here again that normally I would frown upon somebody multiplying both sides of an equation by a variable expression because you don't know if that variable expression is 0 or not. However, we know it's not 0 because the original problem that was given to us has x just as a single argument of a logarithm, which means x can't be 0. Finishing this out, scroll down here, we get the following. This implies that 0 is equal to x squared minus 2x minus 3. Again, that was just from us subtracting 2x from both sides. And this should factor. So we're going to try to factor here. And you get 0 is equal to x minus 3 times x plus 1. And you have two options for x. Either x is going to be 3 or x is going to be negative 1. So let's go ahead and see if either of these answers get thrown out. You can actually pretty quickly see that because of the original equation, because one of our arguments is just x, it cannot be 0, nor can it be negative, and yet we get to an answer that has a negative value, so I get to throw that one out immediately. That's a very fast check. The other one is not such a fast check. You still have to check it though. So we're going to go ahead and go back to the original equation, and we're going to plug in 3 to that original equation, so log base 2 of 3 squared minus 3, so that's 9 minus 3, or 6. And I'll move the other logarithm over as well. And the question is this going to equal, it was supposed to be a question mark, but it obviously did not work out for us. Is that going to equal 1? And again, using a property of logarithms, you can glue these two together, 6/3. Again, is that equal to 1? And 6/3 is just 2. Log base 2 of 2 is definitely 1. So yep, that is totally equal to 1. We're okay. So therefore, that solution of x equals 3 is actually a solution. The other one is what we call an extraneous solution. So that is how you would do that. You do have to check your work with logarithms. Some wacky things can happen, so be very aware of that. Let's go ahead and try this example just for more practice. And this example can throw people off because it looks like it's not solvable. When people initially look at this, they want this. They think it's, in fact, I originally thought this was a typo. They think there should be a power of 5 in there so that it looks like some object squared minus the same object plus 4, but it's not. This is not a typo. Trust me, I thought it was at first, but it's not. And I typed the problem. Just pretend as though or assume that this problem is correctly written. Because the arguments are not the same, and because this is not just a straight natural log, it's a natural log squared. In fact, let me showcase that. That notation just means we have the natural log of x and it's being squared. Okay. Because the arguments of the natural log are not the same, or more, well, I'll just say it that way, then we cannot assume that this is quadratic in nature. In other words, it's not like a u squared minus u plus 4, because the arguments, these two guys right here, are not the same. So the pictures are not identical. You can't do that. But they can be made the same. If you recall, you can take, if every part of the argument of a logarithm is raised to a power, the same power, you can take that power to the outside of that logarithm, and this will actually put this equation in a form that is quadratic-like. This will be the natural log of x being squared minus 5 times that same picture, natural log of x, plus 4. So notice these two pictures, natural log of x and natural log of x, are the same. So you could go ahead and do a u substitution here. So let's do that u sub. We're going to let u equal the natural log of x. You don't actually have to do this u substitution, but I find that most people prefer it, to be honest with you. It just makes it look cleaner, doesn't it? And of course, this will factor. So let me say this implies via a substitution. And then now we're going to factor. So we get u, what is it, minus 4 minus 1? Yeah. And of course, that will imply that u is equal to 4 or u is equal to 1. Now remember, we did not start with u's, so we're going to go ahead and resubstitute what u is. So u is natural log of x, so natural log of x is equal to 4, or the natural log of x is equal to 1. And solving for x in both cases, the natural log, by the way, or any logarithmic function, has a domain of all real numbers. So both of these right now are realistic answers. So we're going to go ahead and continue forward here. We get that x is e to the 4th or x equals e to the 1st. Those are our two possibilities. Now that we've reached those two possibilities, let's go ahead and check them. I go all the way to the top, and you may think that it's kind of bulky to check these, but it's actually not too terrible. It's okay. It's not the best, but it could do. Let's actually take the e first. So x equaling e. We're going to check that. If you substitute in e, you have the natural log squared of e minus the natural log of e to the 5th, and then plus 4. Well, the natural log of e is 1, so you have 1 squared, minus a natural log of e to the 5th is 5, and then plus 4. Well, that's negative 4 plus 4, that's 0. That works out. Now you can check x equals e to the whatever we got, 4th. Again, you have the natural log squared of, now it's e to the 4th, minus the natural log of e to the 4th to the 5th. E to the 4th raised to the 5th. And then plus 4. And let's see, the natural log of e to the 4th is 4. And we're going to be squaring that. Minus, remember, powers to powers multiply, so this is actually e to the 20th. Natural log of e to the 20th is 20. And then plus 4. 4 squared is 16, minus 20 is negative 4, plus 4 is definitely 0. That works out. So both answers are fine. Notice how quickly I went through and took care of the substitution. I was able to check it very, very quickly. And it's because I'm assuming that you have plenty of experience with logarithms. This is not your first rodeo with logarithms. You've actually fiddled around with them for years, actually, at this point. And so I assume that's a pretty strong assumption since you're in pre-cal. But if you find that you're struggling with logarithms, you can search the web for videos. I do have some videos from Algebra 2 for dealing with logarithms. So you're always welcome to view some of my older videos. But I don't have any videos in this series that are really a full teaching series of logarithms. Let's try a different example. Again, I'm trying to get you exposed to all different styles of pre-calculus level examples. And in this case, you're adding 3 logarithms that are completely different bases. And normally, you cannot do that. It is very, very much impossible to add, or it seems very impossible to add logarithms with different bases. However, there is a property of logarithms that I don't use that often, but in this case is incredibly powerful. And that property is the change of base property. I'm going to write it in blue over here. So we can change any logarithm that we want. So in this case, I wrote log base b of x. You could change that to log base any other base you want. Remember, bases of logarithms must be positive and not equal to 1. But other than that, you can change it to any number you want. So you could change it to log base 10 if you wanted to. So you would write that as log base 10 of x divided by log base the same 10 of b. That is a change of base property. And that is from your Algebra 2 course, but it's rarely used, to be very honest with you. But here's a case where you can use it. And this is how obscure mathematics can get for people at times, because you learn an obscure property like that you may use only in the one section you learned it in several semesters, if not years ago. And then all of a sudden it creeps up to be critical to remember within a problem. That's just how mathematics goes, and that's why a lot of people have a hard time with mathematics. Their foundation is shaky and all that fun stuff. So trust me, I know, I understand. But it looks as though I'm going to, what I would like to do is change all of these either to base 10 or to base 2. I think base 2 is fine, so I'm going to change all of them to the base 2. You essentially just pick one of the bases and change everything to that base. So I'll choose base 2. So the first one is fine, log base 2 of x, plus the second one will be written as a fraction, log base 2 of that x, divided by log base 2 of 4. And you can see why I chose to do log base 2, by the way, because log base 2 of 4, that's 2. So that's a very nice way of writing that. And the last one is log base 2 of x divided by log base 2 of 8. And again, you can see why log base 2 was a good choice, because log base 2 of 8 is 3. So I'm going to go ahead. Oh, by the way, I should justify this and just say I'm using change of base. It's not that I expect my students to write out every step of the way, every justification like this, but I like to do it in lectures so people know what I am doing. This will imply log base 2 of x plus 1/2 log base 2 of x plus 1/3 log base 2 of x is equal to 11. Now the question you might have is, how did I get the 1/2 and the 1/3? That is because, again, log base 2 of 4. You're asking yourself, what power would you raise the number 2 to become 4? Well, 2 squared would become 4. And this one is asking the same style of question. What power would you attach to 2 to make it become an 8? Well, 2 to the 3rd is 8. So that's why it's 1 over, because they're in denominators, but that's why I get the 1/2 and the 1/3. All right. So at this point, several ways to go here, I actually do what a student once told me is called fraction busting, which is I just want to get rid of all these fractions rather than adding them up. I just want to multiply both sides of this equation by the LCD. So I multiply both sides by 6, which is the LCD of that equation. So I get 6 times the log base 2 of x plus 3 times log base 2 of x plus 2 times log base 2 of x is equal to 66. Remember, you're multiplying both sides by 6. And that makes it nice because you can just add up those numbers. 6 plus 3 plus 2, well, that's 11 of those log base 2 of x's, and they each equal 66. Divide by 11. And then finally, finish solving this by doing that circular argument. 2 raised to that 6th power should equal the interior. Let me write that down. 2 raised to the 6th power should equal x. And 2 to the 6th is 64. So that implies 64 is equal to x. All right. And so some people will also ask, shouldn't I check that answer? Yeah, I suppose you should. I happen to know it'll work, but I'm just going to say it out loud. If you imagine these are 64s. Whoops. 64 and 64. I don't want to really take forever doing it, so I'll just ask. 2 to what power is 64? Well, 2 to the 6th power, that's what we just said, plus 4 to what power is 64? Well, 4 to the, what is it, third power? 4 squared is 16 times another 4 is 64, so 4 to the third, plus 8 to what power is 64? 8 to the second power is 64. 6 plus 3 plus 2, definitely 11. So I know that that is the actual answer. When you check your work, at least for me, I don't expect you to rigorously write down every little step. You could just do a quick mental check. You'll pay if you don't check your answers. I'm just letting you know. It will be a cost if you don't check your answers, because inevitably there'll be some type of equation that has no solution, or you get answers that are extraneous. So not checking will cause errors. So it would be bad if you didn't check your solutions, but I don't really force students to check their solutions. It's up to them if they want to. Now, this last example is really an exploration so we can see something that I demonstrate within calculus. In fact, in Calc 1, my students just did this style of problem. So let's take a look at this. Logarithms are very, very slow growing, but they'll eventually attain any level output that you desire. So if you want the logarithm to eventually hit a height of 1,000, it will get there eventually, but it takes a long time. So let's go ahead and let our function equal the natural log of x, and we're going to solve f of x is greater than 2. So this is what we call logarithmic inequality. So we're going to go ahead and solve the natural log of x is greater than 2. That's what we want. Well, if you do that circular argument, the inequality will still hold. So this will imply that x must be greater than e to the second. Let me show that circular argument. There's a little hidden base e there, so e to the second and x are related. It's not an equal sign, it's actually less than, so e to the second is less than that x. So x must be greater than e to the second. So that's a pretty nice, easy solution, right? Okay, well, what does that mean? It means for that function, for natural log to get to a height greater than 2, for the outputs to be greater than 2, the inputs have to be greater than e squared, which is roughly around 9, a little bit less than that. Now let's ask, what if I want to know when the natural log is bigger than 100? Well, same idea. We'll just say we want the natural log to be greater than 100. Doing that circular argument, again, base is e raised to the 100th, oops, that's not an a, it's an raised to, that's a caret, that's what we call it. E raised to the 100th would have to be less than x. So let's see, that implies x is greater than e to the 100th. E to the 100th has to be less than x. Wait, so what this means is that if I want the natural logarithm to get to a height above 100, or if I want the outputs to be greater than 100, I need my inputs, my arguments for the natural logarithm to be huge. E to the 100th power, go ahead and grab a calculator and try to figure that out. It would break your calculator. That is a super large number. So if you try it, for example, in Desmos, you will see, actually, let me shrink this up a little bit because I had it off screen, but you'll see that number, e to the 100th, is roughly 2.7 with about 43 zeros after it. Okay, so it is a massive, massive number. It's really inconceivable. It's much more beyond our human intellect. We cannot do that. And that's the number you have to get to so that the natural log reaches a height of 100. So when I say that the natural log grows very slowly, that is no lie. It takes a long time to get to a height like 100. So let's go back to the problem here, and now we're asked to let g of x equal the natural log of the natural log of the natural log of x. It's a composition of natural logarithms. Compositions are something we've talked about already in this course or in this video series, so that should not be unfamiliar to you. However, a description of what's happening when you take a natural log and plug it into a natural log, and then into that plug a natural log in. You have a slow growing function, and into that you're putting in a slow growing function, and into that you're plugging in a very slow growing function. In the end, this function will take forever to grow. Now, forever is the wrong word, but it takes a long time for this to grow. So let's see how long it takes for this function to reach just a height of 2. So I'm back over here in Desmos. I'll just delete this out and I'll call it g of x, and I'll say that's the natural log of the natural log of the natural log of x. Now, I'll go ahead and zoom out of that, and let me move this over here. Here's it does look like a natural log, by the way. I'm going to go ahead and turn off the background grid here because that always bothers me. And I'll put this in projector mode as well. And our question is, how long will it take for that function to reach a height of 2? So I'm going to graph y equals 2. That's that blue line right there. So here we go. Let's go ahead and find out how long it takes to climb to that height. Now we're already at x equals, you can see on the screen, around 60. And the red curve is the natural log of the natural log of the natural log of x. And we want those y values to reach a height of the blue curve, which is y equals 2. And as I kind of scroll over, now we should know it takes a while because it took e to the, well, actually, it should take a while, right? Well, you can see if I keep doing this, it just doesn't seem to happen. I'm going to scroll over as far as I can. And actually, we're currently at around 4 million. That's the x value right now. I just went ahead and paused the video and advanced a little bit. And you can see the graph is only halfway to reaching the height of 2. So at 4 million, we're still not even to a height of 2. You could see that this is an incredibly slow growing function. What you prove in calculus is that this actually will eventually reach a height of 2. Not only that, but in calculus, you'll prove that this function will eventually go to any height you want it to. So let's go ahead and see how that's done. So we're back here, and we just want to use algebra to solve, hey, when is that function greater than a height of 2? So again, I'll just go ahead and write that down. We have the natural log of the natural log of the natural log of x, and we want that to be greater than a height of 2. Well, if you follow that argument, the circular argument, that will tell us that e squared, let me write that down, e squared must be less than this stuff inside, must be less than the stuff inside. Well, you can see there, it's going to be yet another circular argument. We're trying to unwrap this so we have only x. So e, again, raised to that number, so e to the second, must be, again, less than that picture. Must be less than that picture, which is the natural log of x. And finally, again, by the circular argument, e to that picture right there should be less than the x. So e to the second must be less than x. Or in other words, to get our natural logarithm of the natural logarithm of the natural logarithm of x to be greater than a height of 2, x has to go beyond e to the e to the e to the second. So what number is e to the e to the e to the second? Well, that number is so large that Desmos can't even calculate it. This is why mathematics done by humans is so elegant. We can do things that normal, like powerful computers, like this is not based on my desktop computer. Desmos has servers working on this, and they can't even compute this. It's because they only have a finite number of places, decimal places in their arithmetic. But this number is so huge, it breaks Desmos. Yet we know what the number is. It's e to the e to the e to the second. While we don't want to write that down, we know conceptually what it is. So this is a great example of why doing mathematics by hand not by calculator, is super powerful. I could just give you a bunch of problems and say, solve this. And if you're used to using calculators or computer, it will break. It won't be able to do it. So there you go. All right, that rounds out our discussion on solving logarithmic equations and inequalities.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.